Traditional databases store and retrieve data by exact matches. Vector databases store high-dimensional embeddings and retrieve them by semantic similarity, the foundational infrastructure layer for RAG, semantic search, and long-term AI memory. Let us examine why vector databases have become the indispensable infrastructure layer for every serious AI application stack. 5 core capabilities distinguish vector databases from traditional data stores and explain why they are essential for AI applications. At the heart of a vector database is the storage of embedding vectors, dense numerical representations of text, images, audio, or any other data object, produced by an embedding model. Each vector is stored alongside its source content and metadata such as document title, creation date, department, or category. This combination of high-dimensional vector and structured metadata is what makes vector databases uniquely suited to AI applications. They can retrieve by semantic meaning while still supporting exact filtering on structured attributes. The defining query operation in a vector database is approximate nearest neighbor search, or ANN. When a query arrives, it is encoded as a vector by the same embedding model used during indexing, and the database searches for stored vectors that are closest in the high-dimensional embedding space. Closeness is typically measured by cosine similarity or inner product. The word approximate is important. Exact nearest neighbor search across billions of high-dimensional vectors is computationally infeasible, so vector databases use index structures that trade a small amount of recall accuracy for dramatic improvements in query latency. The indexing algorithms inside vector databases determine how efficiently similarity searches can be executed. HNSW, Hierarchical Navigable Small World, builds a multi-layer graph structure where each layer is progressively sparser, enabling logarithmic time navigation from coarse to fine resolution. IVF, Inverted File Index, partitions the vector space into clusters and restricts search to the most relevant clusters. Both approaches dramatically reduce the number of vector comparisons needed for each query, enabling millisecond latency search across millions or hundreds of millions of vectors. Pure vector similarity search can surface the most semantically similar results, but enterprise applications almost always need to constrain results by structured criteria as well. Metadata filtering allows queries to specify conditions. For example, retrieve only the most relevant passages from documents published after a certain date, belonging to a specific department, or tagged with a particular product category. This hybrid capability, semantic similarity search combined with structured attribute filtering, is what makes vector databases practical for real-world business applications rather than academic benchmarks. Enterprise AI applications must scale to meet growing data volumes and query loads without sacrificing latency or accuracy. Modern vector databases are designed for horizontal scalability, distributing both vector storage and query processing across multiple nodes. This architecture allows organizations to start small and scale incrementally as their AI applications grow. Leading vector database platforms such as Pinecone, Weaviate, and Crant support managed cloud deployments that handle sharding, replication, and fault tolerance transparently, allowing engineering teams to focus on application development rather than database operations. 4 essential terms that every practitioner needs to understand when working with vector databases. Approximate nearest neighbor search is the algorithmic heart of every vector database. Given a query vector, ANN search identifies the k-stored vectors that are most similar without comparing the query against every single vector in the database, a process that would be far too slow at scale. ANN algorithms achieve this by building index structures that allow the search to navigate directly to the most promising regions of the vector space, skipping vast portions of the data. The result is sub-millisecond query latency, even across hundreds of millions of vectors, at the cost of occasionally missing the absolute nearest neighbor, a trade-off that is almost always acceptable in practice. HNSW, Hierarchical Navigable Small World, is the most widely used ANN index algorithm in production vector databases. It works by constructing a layered graph where each node represents a stored vector and edges connect vectors that are close together. The top layers of the hierarchy are sparse, enabling fast coarse navigation, while lower layers are progressively denser, enabling fine-grained local search. During a query, HNS enters the graph at the top layer, navigates greedily towards the query vector, and descends through layers until it identifies the approximate nearest neighbors. HNS delivers an excellent balance of query speed, recall accuracy, and memory efficiency. The embedding store is the foundational persistence layer of a vector database. When documents are indexed, an embedding model converts each chunk of text into a dense vector, typically 768 to 4096 dimensions depending on the model, and this vector, together with the original text and any metadata, is written to the embedding store. The quality of the embeddings stored in this layer directly determines retrieval quality. Embeddings from more capable models capture more nuanced semantic relationships and produce more accurate search results. Selecting the right embedding model for the content domain and retrieval task is one of the most important architectural decisions when building a vector search system. Namespaces are a practical organizational feature that most enterprise vector databases provide. Within a single vector database instance, namespaces create isolated partitions that keep different sets of vectors separate. This is essential for multi-tenant applications where each customer's data must not bleed into other customers' search results, and for applications that manage multiple knowledge domains, such as a product documentation namespace and a support history namespace, that should be searched independently. Namespaces allow a single vector database deployment to serve many logical use cases without requiring separate database instances for each one. Let us now look at how vector databases are being used as the foundational data layer across modern AI application architectures. Vector databases underpin some of the most impactful AI applications in production today, from knowledge retrieval to personalization. RAG, Retrieval Augmented Generation, is the most prevalent production use case for vector databases today. Organizations index their internal documentation, product manuals, policy libraries, and knowledge bases into vector stores such as Pinecone, Weaviate, Chroma, or Quadrant. When a user submits a query to the RAG application, the vector database retrieves the most semantically relevant passages in milliseconds, and those passages are supplied as context to the language model to generate a grounded, accurate response. The vector database is the component that makes RAG performant and scalable. Without efficient semantic retrieval, the RAG architecture cannot function at production scale. AI agents, systems that autonomously plan and execute multi-step tasks, need a form of long-term memory that persists across conversations and sessions. Vector databases serve as this memory layer. Each interaction, learned fact, or completed task can be stored as an embedding in the vector database. When the agent needs to recall relevant past information, it queries the memory store semantically rather than by exact key. This gives agents the ability to build up knowledge over time, recall contextually relevant prior interactions, and maintain continuity across long-running tasks, capabilities that are essential for enterprise agentic applications. Recommendation systems are one of the original applications of vector similarity search, predating the current wave of generative AI. By encoding users and items, products, articles, videos, courses, as embedding vectors that capture behavioral patterns and content characteristics, recommendation systems can identify the items that are most similar to a user's preferences or most similar to items they have already engaged with. Vector databases provide the infrastructure to execute these similarity lookups at low latency across product catalogs containing millions of items, enabling personalized recommendations at the scale required by consumer and enterprise platforms. Large organizations accumulate vast repositories of documents, contracts, research papers, and customer communications that frequently contain near-duplicate content, documents that are highly similar but not identical. Traditional exact match deduplication misses these near duplicates. By encoding documents as embedding vectors, organizations can use vector similarity search to identify all document pairs with similarity above a threshold, enabling systematic deduplication, consolidation, and compliance auditing. This application of vector databases is particularly valuable in legal, regulatory, and research contexts where duplicate or superseded documents can create compliance risks. Let us bring together the essential points from our exploration of vector databases. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.